All right, everybody, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360 Control Systems class. Today is our 26th lecture. And this is our also the very last week for lecture. Okay, next week is obviously the final week. So today we're going to continue our state space representation, and we will study some specific detailed operations and try to convert between the time domain and frequency domain representation modeling. Okay, and also at the end of the lecture we will review the midterm 4. Okay, very last exam. Okay, so today we're gonna review that. All right, can you guys hear me well and also being able to watch my screen? All right, thank you, Noah.
Yep. Yeah.
So thank you, folks. Let's start. So let's review a little bit the basic concepts of the state space representation. Okay, I'm using double S to represent the state space. Okay, this is a time domain. First of all, this is a time domain modeling. This is time domain modeling. You need to understand. We have been studying and using the frequency domain, or say S domain transfer function through the entire semester. Now, at last, we are trying to learn a time domain modeling method, okay, which is a tool for advanced control system class. Okay, this is first thing you need to understand. And then inside of the state space, we actually just have two things. One is, what is it? SE is what? And then plus OE. Anyone remember what they are standing for?
Equation and output equation.
Very good, too. Thank you. State equations and output equation. Right? And state equations are a bunch of equations, simultaneous equations, bunch of them. And they're actually dx1 dt equals to what? dx2 dt equals to what? And then so on and so forth. Right? Bunch of equations. Left-hand side of these equations is first order derivative of the x. Who are the x? Who are these x? Anyone remember? Who are these x? Or say we are using x to represent what? State variables. Okay, state variables. SV, okay, state variables. And the first order derivative of the state variables equals what? What we call this? This is what? Linear combination of what? X. These are x again, they are state variables. So linear combination of state variables. And who is u then? Letter u is what? Input. Yes, input. So first order derivative of state variable is equals to linear combination of state variables and input. And this is the state equations, right? This is the state equations, and then simultaneous equations. Okay. And output equation is what? Output equation is just the output y. The output is represented by y, letter y. It equals what? And also linear combination of state variables and input. Output is equals to linear combination of state variables and input. Okay, this is how we see the state space representation. State equations, bunch of simultaneous equations, and one output equation. One output equation. Why one? Because we are studying what? Single input, single output system, SISO. A single input is reflected by what? Single input U. You see here? We don't have U1, U2, and etc., right? Only one U. So single input. Right? Single output, how can we tell that? Well, single output Y. We don't have Y1, Y2, etc. either, right? Single input, single output. Input is U, output is Y. Right? This state equation, output equation, and we also always use what matrix operation to represent the state equations and output equations. What they look like? Capital X equals to A times capital X plus B times U. Capital Y equals to C times X plus D times U, right? So you can easily tell this is state equations, plural. This is output equations. And where the X is what? Is just equals to the state variable vector, right? And equals to state variable vectors. And U is just the input. Y is output. And here, the dot here on top as a hat is actually representing the first order derivative. So how to represent second order derivative then? Two dots, correct. Okay, two dots, correct. And like this. Second order. Okay, this is equivalent to dx square d square x and over dt squared with respect to time t. Okay, the second order. One dot means first order derivative. Okay. So state equations and output equations. That's it. These are the things we learn. Of course, we have names and the dimensions, specific dimensions for A through D. They are different metrics. Right? Be very careful what dimension they're supposed to be. Okay. Another thing you need to be very clear is how many state equations here, or say the number of state equations equals to what? The number of state variables, right? And both numbers are determined by whom? Anyone remember? How can you tell how many state variables and how many? Very good, very good. A system order. System order. Great. And further, the system order is also equals to what? The order, or say the highest order of the differential equation. Of the system. We will see. Maybe we'll see this. Okay, the system order. And be very careful. We are not talking about a system type. Okay, system type is used to determine what? Steady state error. That's different. Okay, system order is the highest order of the differential equation and also equals to a highest order of the closed loop transfer function denominator polynomial. Denominator polynomial of closed loop transfer function. Okay. This is the system order. So remember this, okay? I'm using the red to emphasize this concept. How many state equations and how many state variables, and they follow certain rule. Okay. All right, these are the basics we need to review. And now let's learn the things we really need to do some calculations, or not a surprise saying that will be assessed in upcoming exam. Okay. What we're going to learn is actually conversion. Okay. Conversion between the frequency domain transfer function and time domain WS. Okay. Obviously, both are modeling methods. One is in time domain, another is in the frequency domain. It won't be surprised that they're supposed to be equivalent, right? You have one, you can find the other, okay? And the back and forth. Okay. This is the thing you need to understand. And now let's first of all learn the first one. Let's begin with from the transfer function to the WS. Okay, one way. Followed by the other way, right? From the WS to transfer function. Let's see how to do it. Okay? It's not very difficult, but you need to exercise some. Okay? The basic idea is very straightforward. From the transfer function, how to find the state space. Okay? How to find it. Anyone has any idea? Best answer so far I received from you guys is from Jeff. Inverse Laplace. Okay. Perfect answer. Almost perfect, I would say. Okay. Here, I'm using red color to write down the idea. Right? The idea is, first of all, of course, transfer function is given, right? Transfer function is given. What do you want to do? Remember, the state space is a rewritten what? Differential equations. So given transfer function, the first step is to find the differential equation, right? And then next, we're gonna choose state variables and rewrite it as Kevin mentioned here. And then to reach the state space. Okay. This is the idea. Does it make sense? And this is the idea. First, you need to have this concept in your mind. So how to find the differential equation? I call it a raw differential equation, right? How to find it? Of course, as Jeff mentioned, it's inverse Laplace. Okay, inverse Laplace, and then you can find differential equation. Okay, it's very straightforward. This is not something new, actually. So let's just directly conduct example here. Yeah, conduct the example here. Okay, the first example. Given a transfer function, very straightforward transfer function like this. Now just find the state space. Find a corresponding state space for the system. Right. This transfer function given is trying to model some certain system, and then we're looking for the equivalent state space modeling in time domain. Everything makes sense. And let's see just how to do it. Okay, follow the procedure like this, Follow the procedure like this. Okay. Now, first of all, we are having a transfer function. Be fully aware that this transfer function is closed loop transfer function. Okay, given the transfer function of the system is it won't be open loop transfer function. Okay, because the closed loop transfer function is complete the entire system transfer function. Okay, closed loop transfer function equals what? What are these? Numerator is what? Denominator is what? Exactly. Okay, it's output over input. That makes perfect sense. This is closed loop transfer function, right? Closed loop transfer function. how to conduct the inverse Laplace transform. Okay. This is actually, once again, not something new anymore. So we got this, right? We have done this, right, in exam 1 or 2. It's not something new at all. We are conducting the cross multiplication, right? And we are seeing the equation now as an equation. And now what we are going to do? Now it's time to conduct the inverse Laplace. 24u, which is the 24 what? Lowercase u, input. Now we are seeing u, remember? It's the input of the state space. So this term go inverse Laplace. Equals to this term, right? And then equals to s cubed times capital Y of s. Of course, here I'm skipping the parentheses of s, but you know both u and y in capital letter are function of s. Right? So s cubed times y equals to what? Anyone still remember? Conduct inverse Laplace on this particular term. What do we end up with? Anyone still remember? And also, if you don't remember, that's okay. But do you know where to find it? Very good. It's a table now, which is the one that our handout ever been given. And from there, we find out this is actually what? S cube is what? What's the inverse Laplace? Result. Does it make sense? Inverse Laplace transform of the S cube is third order derivative, okay, of lowercase y this time, of course. And of course here, we're assuming all initial values are 0. And follow same idea, d square dt of y, and then plus 26 dy dt, and then plus 24 lowercase y. I believe most of you guys have impression we have done this, okay, in the previous exam, not something new. Now we have the raw, once again, I call it raw differential equation. The raw differential equation. Here. And from now on, it's the new thing you need to learn. How to choose the state variable and how to rewrite the raw differential equation into the state space. Okay, this is new. Now, starts now. Okay, start now. How to do it? Okay. We are choose state variables as successive derivative. And be clear, we need how many state variables SV we need? How many, everyone? How many we need? Very good. Okay, Kevin is listening. Kevin is listening. Yep, 2 as well. Very good. Remember, this is a very important thing. At the beginning, no one can tell you how many you need. The number of state variables you need to tell yourself, and therefore you know how many state equations you're gonna write, right? This is very, very important. Okay, so at the beginning, you need to understand how many you need. Okay, so it's all up to the system order, highest order of derivative, which is 3. Okay, that's why you need 3 state variables and therefore 3 state equations. Okay. After knowing this, and then you go ahead to do this. Okay, this is, I'm using the black. Let me use the black to emphasize the, because once again, this is new thing. First, you need 3, right? And we are using x to represent the state variables. Okay, then you just write down x1 through 3, right? Then what matter is who are they? How to choose them? Listen carefully. You're giving output y to x1. Okay, x1 just equals to output y. Remember, do this first. x2 as successive derivative, which means derivative of y with respect to time t. x3, very easy. Second order derivative of y with respect to t squared. Okay. And further, you notice that what? x2 is just equals to x1's what? Derivative, right? And for the same reason, x3 equals to x2 derivative. Does it make sense? And if this is fine, then keep them there. Okay, keep them there. You're gonna use them very soon, very soon. Based on your choice of state variables, guess what? You're able to write state equations. Okay, you're able to write state equations. Let's see how to write these equations. State equations, how to write it. It's actually very easy. First of all, you understand you need 3 state equations, right? Because same number as the state variables. Next, what you know is left-hand side of the state equations are what? First order derivative of the state variables, right? So dx1 over dt equals something. Then dx2 dt equals something. dx3 dt equals to something. These are 3 state equations. Does it make sense? This is the definition of state equations. It's not for any individual problem yet. Okay, this is just the definition. State equations are defined in this format. Okay, left-hand side of the state equation is definitely the first order derivative of the state variable. So it must be like this. Right? And then let's see what is the first one, right-hand side of the first equation here. First order derivative of x1 is equals to what? Very simple, isn't it? x2, how about that? It's out of here. First order derivative of x1 equals to x2. Very simple. Then second equation, the derivative of x2 equals what? What this guy is. Here we go. Kevin is following well. x3, right? Very easy. A little bit troublesome is the very last one. Derivative of x3 equals what? Anyone has any idea? Any thought? Now listen, here, how to do this is a little bit tricky. As remember to do this. Okay, so derivative of x3 is this guy, right? The derivative of this guy is equals to d cubed y dt cubed. Does it make sense? Because of the here. You're doing one more derivative on both sides, basically, on here. You end up with here, right? But from here, the third order derivative of y with respect to t equals to what? How to find it? You go back to here. Okay, you go back to the raw differential equation. You're basically looking for this guy, right? Which is equals to what? Equals to negative 9 d squared y dt squared minus 26 dy dt minus 24y, and then plus 24u. Does it make sense? This is the result from the raw differential equation. This is the result from the raw differential equation. Okay. And then now let's take a look at back these three equations. Okay, you will see the format thing. Okay, first of all is the first equation here, okay or not, and why? Any comment? First equation is okay or not? In other words, can we call the first equation here as a state equation? Is it? Anyone?
We have to fill zeros with the remaining x1, x3 parts of that matrix, don't we?
The correct.
The coefficients, yeah.
John is correct. Okay, John is correct. However, is this x2 okay then? That's actually the point. The x2 is perfectly fine. Why is that? Why is that? Let's take a look at the. This is the notes we had at the very beginning of today's lecture. The state equation must be of first order derivative of a state variable equals to a linear combination of state variables and input. So if you're imagining A1 in this particular example is 0, A2 is 1, A3 through AN and AN plus 1 are all 0. And then guess what? This equation is fine, right? Left-hand side, first order derivative of a state variable. Left-hand side, right-hand side is state variable. Even though just the one state variable, that's fine. Your constant might be 0. These A's, these C's, they all could be 0. So the first equation here is fine. Okay, it's fine. Once again, derivative of x1 equals to state variable. That's okay. If you are input, you can have input. If you don't, that's fine. The coefficient of the input means 0 then. That's okay. For the same reason, how about second equation here? Perfectly fine, isn't it? For the same reason. It's about, once again, it's about rewrite following the pattern, or say the format, right? So this is okay. These two equations are absolutely okay. Yeah, they're absolutely okay. How about the third equation here? Any comments?
They should be replaced with the x1, x2, and x3, or I guess respectively, right?
Very good, very good. Okay, that's the correct solution. In other words, look at this equation. This equation is absolutely not good yet. It's correct equation, however, it's not ready to be a state equation yet. The reason is very simple is, again, because of the format. Left-hand side of equal is derivative of one of the state variable. Okay, good. Right-hand side is what? Derivative of output. It's not even close, right? They're not state variables, and they're not input either. So definitely these y terms are not okay, because once again, they are not fitting the required format. So we need to replace them by what? Keep this here, and first two equations, fine. Third equation need to be rewritten. In other words, like John mentioned, we are replacing those derivative of y and y itself, these three terms, in terms of x1 through x3, right? So how to replace this -9 second order derivative y? What is it? How to replace this guy, this term? Negative x3. Correct. Very good. And then what's the next? 26 derivative of y. What is it? What is the second term here? What is this one? Negative 26 what? X2, right? Third term is what? Negative 24 x1, right? Okay. So these are the first three terms. The very last one, the very last plus 24u. How to replace this guy? The last term, 24u. What we do?
Nothing.
Very good. Excellent. Why nothing?
Well, I mean, that's an input constant, so.
Exactly. Okay. We are okay with input. We are okay with state variables. And x3, 2, 1, they are state variables. U is input, so perfectly okay now. And this is how we end up with the state equations. Now, this is how we end up with state equations. Okay. Next is the output equation. Okay. How to find the output equation? Output equation is even easier. How to find the output equation from here? Any idea? Output equation. It's once again linear combination of state variables and input. The output equation is equals to what? Output equation, without knowing anything else, is definitely y equals something. Just as simple as this. What matters is just the right-hand side of the equal. What is it? Anyone knows? Anyone realize output equation is what?
Can we?
Excellent. Sawyer is right. Yeah, just why does the equals to x1? Done. Just simple like that. Because once again, it's just a format. You match the format, you're good. Left hand side output, right hand side state variables and/or input. Well, you have x1 here. You got this equation. It's not violating any rule. Not violating any format. Done. Just as easy as this. Just as easy as this. The key is here. Back to here. Black color is the key. Black color is the key. How you choose the state variables and how many you need. And the last but not least, the matrix. Okay, we need to write them into matrix form. A matrix form is what? A matrix form is like this, right? You can x dot equals to what? A matrix times x times a matrix times u, and then y equals to a matrix times x plus a matrix times u. I give you guys 1 minute to write this yourself. Populate these metrics 1, 2, 3, 4. I mean A, B, C, D, 3, 4 metrics. Give you guys 1 minute to do this yourself. All right, let's see the solution here. So first of all, you need to understand this is the 3 by 3 matrix, right? Yeah, 3 by 3 matrix. This is what? 3 by 1. This is what? 1 by 3. This is 1 by 1. These are the dimensions. Why they matter? The dimensions are telling you how many entries you need. So this is 3 by 3. First row is what? 0, 1, 0, right? Second row is 0, 0, 1. Last row. Anyone got last row here? In order, they are. Anyone? No. Last row here is trying to write the third equation here.
Sorry, I was looking at the wrong one.
Yep. Anyone got the last row entry?
-9, -26, and 0.
Nope. Sawyer is correct. Okay, Sawyer is correct. Okay, so be very careful here. Be very careful here. In other words, -24 here, the first of the entry of the third row is whom? The coefficient of whom? x1, which is here. Okay, it's up to which coefficient, because this guy is x1, 2, 3, right? Okay, you need to understand this. Is this follow certain order? Okay, so -9 here is the coefficient of x3. Okay. For the same reason, what is it? 0, 0, 24, right? And to y here is 1, 0, 0. That's very easy. And then what is the matrix D then? Anyone? 1. Nope. 0. Here we go. Noah is right. 2 is right too. Okay. 0. Output here is there's no input here. Of course, it's 0 then. Okay. This is, the output is not directly contributed by the input. That doesn't make some sense. This description. This is the example 1. This is example 1. This is example 1. And there's some details. Yes, you need exercise to get used to it. Okay. And then after that, you should be okay. It's not something very difficult. But without exercise, no, you can't do it right. Okay, you can't do it correctly. Without exercise, no, you can't. Okay. Any questions regarding this first example before we are doing example 2, actually? Any questions? All right, if that is fine, then we go to a more complicated scenario. Okay? We go to more complicated. And can anyone tell why this is more complicated? What's the difference from example 1? What's the major difference? A top, what's the top? A numerator, right? The problem is here. Not a constant. The numerator here is not a constant. So see how to deal with this. Okay, you need to be very careful because how we deal with this is different from example 1. Okay, this is something new. You need to be very careful. First of all, due to, I call it non-constant. I don't know if this is a proper English, but hopefully you understand what I mean. If due to the non-constant numerator in closed loop transfer function, you need to do this. Separate numerator and denominator to find double S. Okay, remember this basic idea. You need to separate them. Okay. Let's see how to do it. How to separate. First of all, these given system you need to understand in this way. Okay, right? First of all, the given system is essentially like this. Does it make sense? Numerator times 1 over denominator is what? It says it's a cascade connection of 2 blocks. The total of them is just a product between them, and it equals to total transfer function, right? And at 2 ends, you have input and output. The trick is in the middle, you have a middle step, call it middle step variable m. Does it make sense? This is the equivalent system, right? This is the equivalent system. Your understanding of this system is like this. Then how we separate them? This is how we separate them, right? We separate numerator and denominator. Of course, result system is equivalent. And then what we do? Take care of them one after another. Okay? Take care of them one after another, following the same procedure from example 1. Okay. Let's go for it. We have first one. So first block. And take care of the first block. We are having m over u equals to this transfer function, right? By the way, this denominator is the result of you expanding this product between these two. Okay, you're expanding it. Nothing but same. And this, if you do cross multiplication, what do you end with? U equals to s cubed m plus 6s squared m plus 10s m plus 5m, right? This is the cross multiplication. Nothing difficult. And then if you conduct a inverse Laplace transform on which what you got is lowercase u equals to d cubed m dt m plus 6 d squared m dt squared plus 10 dm dt plus 5 lowercase m. Does it make sense so far? This is the result after the inverse Laplace transform. This is the result of the inverse Laplace transform. And based on which, we move on. Very tricky. Okay, from this differential equation, this is nothing but the raw differential equation. Now, time to choose state variables. How many we need this time? 3 again. 3 again, correct. They're respectively x1, x2, and x3. Very straightforward. Now x1 is equals to what? Be very careful. X1 equals to what? Based on the example 1, x1 equals to what? Whom we get? M. Very good. Very good. Okay. Be careful. X1 is not y anymore. Okay. Now we're dealing with y. We're dealing with m and u, not y and u, right? So x1 is given m, not y. Okay. X2 is what? X1 dot, or say m dot, right? X3 is what? X2 dot, which is also equals to m double dot, right? Does it make sense? This is the most important step. After some exercise, it's become very easy. And after having these state variables, directly we can come up with the state equations. State equation, once again, is x1 dot equals what? X2 dot equals what? X3 dot equals to what? You know this before looking into any details, right? You know these SEs are just x1 through x3 dots. The x1 dots is very easy, just x2, right? So you get it from here. 1 dot x2. X2 dot is x3. We got it from here. These two are very easy, very easy. Third one is what? X3 dot. X3 dot. Well, you need to go back to here, right? X3 dot is equals to, first of all, is m3 dot. Doesn't make sense. Because here you do one more derivative on both ends. You got f3 dot equals to m3 dot. And for the m3 dots, you need to derive from this raw differential equation, right? What do you got? -6 m 2 dots minus 10 m dots minus 5 m plus u. This is derived from, again, the raw differential equation. Just equals to, and then replace the m's. M dots, they cannot appear in the state equation. You have to replace them by x or u. Right? -6 m double dots is what? -6 x3. M dot is x2. M is x1. Keep the u here. Keep the u untouched here. So state equation's done. State equation's done. Okay, this is the first block. We're done here. Okay, state equation done. Second block. Okay, remember, this is the first block. Okay, now so far we have taken care of the first block. Now let's go back to the system and then take care of the second block. Second block. Second block is whom? Second block is here. Between m and y. Okay, be very clear. Between m and y, what you have is y over m equals to this transfer function, which is s squared plus 3s plus 7. And cross multiplication equals to y equals to s over m plus 3sm plus 7m. Then you're applying inverse Laplace transform on it. And then what do you got? Output y equals to e squared m dt squared plus 3 em dt plus 7m. Right. And these are nothing new. These are nothing new. Just to be very careful. Now we are talking about y and m. Y and m. Not directly anything to do with u. Okay. This is the raw equation, which give us the output equation. How to rewrite this raw differential equation to the output equation? Once again, left-hand side is y, output itself, equals to what? State variable x or u, right? And/or u. How to do this? How to do this? First, how to replace this guy? This term is replaced by whom? Very good. x3, right? Noah is right. It's nothing but x3. Why is that? You have chosen the state variable from previously in black color. Okay, black color part is the most important part. This is what pretty much m2 dots, right? M2 dots go back to here is equals to x3, state variable. It's okay. So x3. For the same reason, second term here is what? 3x2, right? 3x2, right? Okay. Because this is m dots, which is here, equals to x2. Right? And the last one, m is what? M is, go back to here. M is what? x1. And then you take a look at the output. Okay, output equals to the linear combination of all of the state variables. without input, but that's okay. The coefficient of input is 0 then. Perfectly fine. So what do you see? You are getting the state equation here and the output equation here. Done. You're done. In other words, by taking care of the first block, you are going to find state equations. Right? And by taking care of the second block, you are going to find the output equations. Okay? So you need to separate them. The last but not the least matrix form is equals to what? Right? It's matrix form. And according to the state equation here, you populate the entry as this. Right? As these. And then populate the matrix C and D as, once again, be very careful which is which. Okay, which is which. You're looking for the coefficient of x1, 2, and 3. Now this is pretty much done. By repeating independently, conducting the example 1 and 2 should be okay with this procedure. Any other questions regarding these two examples? One of our midterm exam problem, right? It won't be surprised that way. All right, if this is okay, then let's just quickly talk about the second way, the other way around, which is, oh no, the bulletin is not here. The bulletin is this. The other way, from the given state space to transfer function. The other way. This is actually new. This is absolutely new. This is it's not like a given transfer function. You know, you're gonna use the inverse Laplace to find the raw differential equation and then go to the state space. But here, the other way, from the state space to transfer function, this is something new. Okay, this is something new, okay? But not difficult though. Not difficult. Just to follow what? A formula, which is output over input. Of course, this is closed loop transfer function. Okay, once again, it's closed loop transfer function. Is equals to what? Equals to C times parentheses S times I minus A parentheses inverse times B plus D. This is the formula. Right? This is the formula. Who are A, B, C, D? Who are they? Because remember, this is given the state space, which means given you a what? A matrix, exactly. Okay, Alex is right. A, B, C, D are the state equation and output equation matrices, okay, in the given state space. So this operation is what? It's matrix operation. Okay, this is matrix operation. These are bunch of matrix. So this is what? Inverse matrix. And inside of this parenthesis, this guy is who? I is what? Anyone knows? Identity matrix. Jeff is right. Very good. Identity matrix. Identity matrix. What does it look like?
A diagonal above one.
Once, very good, very good, very good. Okay, most of you guys, many of you guys actually know. Once along the main diagonal and zeros are elsewhere. Very good. Zeros elsewhere. Very good. But therefore, s times, this is s, okay? This is nothing but s, okay? S times I equals what? We have s times I, right? So si times I equals what? S along the main diagonal, zeros elsewhere, right? Does it make sense? And then this Si minus subtract the matrix A, whatever it is. Okay. Here, Kevin wants to make sure the equation is here. So the matrix C times parentheses, or say times the inverse matrix of Si minus A. And then further times matrix B, and then at the end plus matrix D. Okay, sure. Okay, this is the equation. So what matters is just the algebra, and instead of this algebra, what might be a tricky part? Inverse, right? This is the only possible tricky part. Only possible tricky part. Only possible tricky part. Inverse matrix. Inverse matrix. Okay, we're gonna go through examples by Wednesday lecture, and by a couple of examples, I think you guys are definitely gonna be ready for this problem. And this is another problem in the exam. Okay, let you know. All right, thank you for attending today's lecture, and talk to you guys all on Wednesday.